Well, good afternoon, everyone. Today we're talking about geometric representations of complex numbers. So, yeah, this is 11-2 and wanted to hit a couple items here. We've seen from before, we have seen the complex axis, and this is the real number axis. This is the complex axis. And when we have numbers like this, they might be things like, I don't know, 3 and 4i. Keep in mind, complex numbers are in the form a plus bi. So if we have 3 plus 4i, that definitely fits the bill. Keep in mind, then we can go over 3 units on the real number axis and then up 4 units on the complex or imaginary axis. Maybe I should say that, imaginary axis. I think that's better. And you can't say, oh, 3 plus 4i, that's 7i. Well, it doesn't work that way. Um, these two can't mix because one's real and one's non-real. If we have a vector such as this, we say that this is a polar angle. And again, just like in the last section, we can have rectangular coordinates and we can have polar coordinates, and we can convert between the two. If you had something like in example 3, oh, before I go there, I probably better review, we'll go to example 3 in a minute, probably better review that cis function. Z equals R cis theta, or alpha, or whatever you have for your angle. We had this earlier in the book, but it's been a while. We haven't used it a lot. Remember, that just means Z equals R cosine theta plus R I sine theta. And oftentimes they'll factor out an R, and you'll see this as Z equals R times the quantity cosine theta plus I sine theta. Hence the abbreviation here is R times cosine theta I sine theta. And this is really useful, especially after having dealt with chapter 10 and all those simplifications for things like this. Okay. So example 3 is kind of a stickler. Raven and I were talking about it today. And yeah, it has some issues. So we better run through that. And thank you to Joseph and Gavin for working on the sound. Hopefully the volume's up on this thing. And if not, you can blame it on them. No, we'll keep tinkering with it until it's perfect. Okay, in example 3, they talk about expressing two vectors in polar form if they're given to you in rectangular form and multiplying them. So a couple of things going on here. The one they give us, this is example 3, and I think we need a little bit of an explanation. Z sub 1 equals 3 plus 3i, and Z sub 2 equals 1 plus I times the square root of 3. And that's just a convention you'll see. Why didn't they say square root of 3i? You could have, but this is the way you see it a lot. And the challenge here is to express Z sub 1 times Z sub 2 in polar form. So I feel like the easiest way to do this one is to express each one individually in polar form. In other words, convert from rectangular form to polar form, and then we'll be able to multiply them and add their polar angles. Okay, so as always, I like to make a little sketch. If you have 3 plus 3i, well, there's 3, there's 3i. It looks something like this. Okay, it would be that location there. So let's think about this. 3 plus 3i. Well, we can use Pythagorean theorem certainly to get r here. So we could say r equals 3 squared, well, r squared equals 3 squared plus 3i squared. And then we can say r equals the square root of 9 plus. Now I know what you're thinking. You're thinking, well, 3i squared is negative 9. But in this case, you need to take the absolute value. So that would be 9 times negative 1. And so you get r equals the square root of 18, or r equals the square root of 9 times the square root of 2. So r equals 3 root 2. And that is that distance of our hypotenuse up here. I'm going to back it up. Man. R equals 3 root 2. And then as always, say to yourself, does that make sense? So we've got 3 here and 3 here. Yeah, because remember, on a 45-degree right triangle, it's 1, 1, and the square root of 2. So this would be 3, 3, and 3 times the square root of 2. So that one's right. That's good. Now let's think about our polar angle here. That would be this cat right there, polar angle, not the polar express. So our polar angle would be from here theta. This would be opposite. This would be adjacent. So that'd be tangent. So we would go arctan opposite 3i over 3. And really, for this kind of a deal, you don't have to worry about the I. It's just that angle. I threw it in there. It's okay. And that equals 45 degrees. You can look on your unit circle or you can use your calculator. But a tangent of, an arctan of 1 is 45 degrees. So life's good. You can also think of it as sine over cosine, sine theta over cosine theta. Either way, you get 45 degrees. So when we come out with that, and we're in quadrant 1 here, we can say that our polar coordinates for that particular coordinates are then r 3 square root of 2 and cis 45. And we have to keep that cis in there because that's where this I is taken care of. 3 square root of 2, that's our r, cis 45. Remember that's 3 square root of 2 times the cosine of 45 plus 3 square root of 2 times I sine 45. That's what that cis is just shorthand for. Okay, and I think I'm even going to celebrate and put a box around that because that's going to help us later. Okay, now let's go a little more quickly on this next part. I could have said that was r sub 1. I'll use a different color to make them look different. So now we can say, and I'll go r sub 2 equals, on this one we have, I can't even remember, I've lost it, 1 plus I times the square root of 3. Okay, let's make a little sketch. So for this one, we've got 1 and the square root of 3. It's there. So r sub 2 equals the square root of 1 squared plus the absolute value of the square root. It's all under the radical of I square root of 3. So r sub 2 equals the square root of 1 plus the absolute value of negative 3. R sub 2 equals the square root of 4. Extend. R sub 2 equals 2. And so that distance is 2. Again, say to yourself, does that make sense? 1, 2, and the square root of 3. I know that triangle from geometry. I'm not going to tell you what it is, though, but you probably already guessed. So if we have a theta here, then we can say the polar angle is arctan square root of 3 I over 1 equals, and you know this one, 60 degrees. So yeah, we're doing good. So our polar coordinates now are then 2 cis 60 degrees. Okay, so we got that. I'll put that one in green también. Okay, so then you probably remember from somewhere, I don't know where, that if we're trying to get a product of two complex numbers in polar form, we, number one, multiply absolute values and we've already taken care of that, and two, add their polar angles. Okay, so we need to multiply their absolute values, which would be 3 square root of 2 times 2, and add their polar angles, which would be 45 degrees plus 60 degrees. And let's see what we come up with then. So we would have 6 times the square root of 2, cis, 105 degrees. And that, ladies and gentlemen, is the product of two complex numbers in polar form. So I hope this is helpful, especially Raven, because we were looking at this earlier and it looked like nonsense in our earlier work. And there is a graph in the book that shows that as a vector. It was kind of cool. Maybe we should take a little time and do that up at the top. I don't know if I can. Maybe I'll group those together first, and then we'll just clone it and carry that up. Can we get it all the way back up to the beginning? Maybe. Oh, this one turned out to be long. Oh, I thought I had a good drawing up there. Never mind. Man, it's terrible. I thought I had a good drawing of those. Anyway, there's one in your book. Check out that drawing. And thanks for listening. I've been at it long enough. Bye.